So it's a pleasure to welcome Bryan Gaensler, today's seminar speakers. Thank you for agreeing to give the seminar at such short notice. So Bryan did his PhD from the University of Sydney in 1998, if I'm right, and then moved to Harvard as a Hubble Fellow, to MIT, and then eventually to Harvard, held Hubble and Clay Fellowships. And then he was in Harvard for a few years before moving back to the University of Sydney as a professor. And he's been here at the Dunlap Institute for the last 4 years. And Bryan, we all know, is an expert on all things cosmic magnetism, which is what he's going to talk to us today about.
Okay, thanks Vishesh. And hi everybody, thanks a lot for coming. So as some of you know, I love magnets. And I know that some of you might not love magnets as much as I do, but maybe by the end of this talk you'll start to change your mind. So I've had a lot of fun working on this over the last number of years, particularly with a lot of students. The students' names are in italics. There's several of them who are here right now at U of T, and some of them who are in the audience as well. So magnetism is something that a lot of astronomers don't like to talk about. And so to sort of ease you into it, I thought it might be better to start talking about magnets here on Earth, since you all are comfortable with magnets. You have them on your fridge and on your credit cards and all that sort of thing. So what you might not appreciate is that magnets play a very important role in life on Earth. The example that you're probably aware of is that birds use the Earth's magnetic field to navigate. We know that some species of birds have these incredible feats of navigation where they travel more than 10,000 kilometers from season to season, and they know exactly where to go. And that's due to lots of things, but part of it is due to them using the Earth's magnetic field. And you might ask the question, well, how do they know? How do they sense the magnetic field? And the answer, as far as we can tell, is that there's actually a molecule in the birds of some of these a molecule in the eyes of some of these birds, and this molecule is called cryptochrome, and it actually has a quantum mechanical response to a magnetic field such that when the bird's eyes are aligned with the magnetic field, it actually sees brighter vision than when it is aligned across the magnetic fields. So the idea is that when a bird's flying, literally their vision lights up when they're flying in the correct direction. And this is part of a much broader area of research called Magnetoception or Magnetoreception, which is a whole branch of biology that studies the ways in which different types of animals have natural abilities to sense magnetic fields. Now, I don't know about you, but every now and then you read a paper in a completely different field, and you read that paper and think, I wish I had done things differently. I want to drop everything I'm doing. I want to redo my PhD thesis, and I want to do this instead. And that's how I felt when I read this paper by Bagol et al. It was published in Proceedings of the National Academy of Sciences, which is a very respected journal. And what they did is they used Google Earth to look for cows. You've probably heard about this already, probably from me, because I talk about it a lot. And what they did is they looked for cows on Google Earth, and when they found a cow, they looked which way the cow was standing. Was it standing this way or that way or this way or something? And this is a great project for summer students. You just get a whole bunch of students and you give them a country each and you tell them to go looking for cows. And what they did is they measured the orientation of the cow with respect to the compass. Now, of course, a cow as viewed from Google Earth is not a complete vector, and that you can't tell the difference between a cow pointing this way and a cow pointing that way as viewed from a satellite. But you can tell the difference between a cow pointing this way and a cow aligned this way. And the methods section of this paper is just beautiful. They corrected for time of day. They eliminated cows that were obviously eating or drinking or being chased by a dog or hemmed in by a fence, and only looked at cows that had virialized cows that had reached some sort of equilibrium state. And here is their main plot from their paper. At each point represents a group of cows showing you which way it aligns. And what's really exciting is that you can see this clear excess in that there are many more cows pointing north-south than pointing east-west. And you might say, oh, well, that's because cows like to be warm, and the sun is either normally rising or setting, and so they orient themselves so that the sun is shining on their sides to maximize surface area. But this is where the hard-working cows of Canada come in. Because if you go to high latitudes, like the cows of Canada, then a cow pointing towards geographic north and a cow pointing towards magnetic north start to diverge the further north you go. And what you can see, and again this is thanks to all the cows at high latitudes, is that here is geographic north and here is magnetic north, and you can actually see a slight offset that the cows aren't lining up with geography, they're actually lining up with the Earth's magnetic field. So you know this was quite controversial at the time, that cows can somehow sense magnetic fields. They repeated the experiment with deer. They looked for in the forest, they looked for places where deer had sort of settled down for the night and measured the orientation of the patch in the snow where the deer had fallen asleep in the winter, and they showed the deer also was sleeping north-south. So obviously this is controversial. One of the questions might be why, and the answer seems to be that cows just like standing aligned with the magnetic field. And so Herd et al. Had a rebuttal. It's a lot like astronomy. What they did is they took the same data set and they analysed it in a different way. They binned the data slightly differently and they used a different statistic and said, we don't see anything at all. And then the original group replied, and in their reply they say, well, now there's a new satellite release from Google and we reanalyze the data, you know, a new data release, and they said the signal's not only there, but it's there even stronger than before. So I guess the jury's still out on whether bovine compasses are a real thing or not, but all I can say is that in my heart I know this must be true. So next time you're driving up to the cottage or down to the US or on the long, boring 401 on the way to Detroit, instead of just sort of concentrating on the road and or listening to the radio, look out the window and look for cows and see what they're doing and do your bit for citizen science. It goes beyond cows though. People have found this all over the place. My favorite study is one on dogs, where they actually followed dogs around a park in some big city and waited for the dog to poop. There's some great pictures in the paper, which my wife said I'm not allowed to show, where involving a dog and a poop and like a protractor overlaid showing you the alignment. And indeed it seems dogs prefer to poop north-south as well. So again, another experiment you can do while walking around Toronto. So in any case, there's a whole bunch of things people have done this with fish and with cows and with dogs and all sorts of other animals. There does seem to be this vestigial evolutionary response that makes different animals prefer to align themselves along the Earth's magnetic field. Turns out that even humans do this as well. They have done experiments in the lab where they have got a magnetic field that they align along the length of a subject's bed and across the subject's bed, and you actually have a different length of REM sleep when you're sleeping aligned with the magnetic field as opposed to across the magnetic field. So rather than the concept of getting up on the wrong side of the bed, I would suggest the problem of feeling like you haven't had a good night's sleep is perhaps sleeping across the Earth's magnetic field. And even more strangely, Lipnicki actually asked people to keep diaries on how bizarre their dreams were each night on a scale of 1 to 5, where 5 is like flying through the air and 1 is sitting in a colloquium. And he correlated that to the level of geomagnetivity at that night on that particular site. And what he found is that when geomagnetic activity is high, people have very boring dreams. And when geomagnetivity is low, people actually have very bizarre, colourful, strange dreams. And it's been speculated through a mechanism that's not entirely understood that the level of geomagnetic strength and fluctuation actually affects the production of melatonin in the brain, and the melatonin actually affects what sort of night's sleep you have. So there's lots of things here, some a bit interesting, some a bit wacky, that suggest that here on Earth we do have a biological response to magnetic fields. Elisa? Well, the problem is I've never been able to find this paper. I see lots of people reference this paper, but it's in some obscure journal from the 80s that's not online, and I haven't been able to find it yet. But once I find that paper, I'll be able to let you know. I guess, that's right. So these are natural magnetic fields. What about artificial magnetic fields? We're physicists. We need magnetic fields for all sorts of things. So now I'm going to start to move towards the astronomy and to give you a sense of the strengths of fields. So let's ask ourselves, magnetic fields are measured in Gauss or in Tesla. The Earth's magnetic field that makes a compass point north, or that used to make compasses point north before we all had GPS, has a strength of about 1 Gauss. And a fridge magnet has a magnetic field strength of 100 or 1,000 Gauss. So put that in perspective, the strongest sustained magnet that exists on the planet Earth is this magnet in Florida. And it has a magnetic field strength of 450,000 Gauss. So maybe 1,000 times stronger than a fridge magnet. And to get that strength, you need quite a lot of work. You have to have almost 3,000 liters of liquid helium, and you have to have a continuous power supply of 33 megawatts to get up to 500,000 Gauss. So that's a steady magnetic field. What if you want to go higher than that? So the highest magnetic field you can get just for a moment, if you don't care if it's on continuously, but just for a moment, is this appropriately named multi-shot magnet in Los Alamos. And they have been able to reach a magnetic field of almost 1,000,000 Gauss just for a few milliseconds. And here is a plot from some of their data. So here's magnetic field in millions of Gauss versus time. And you can see it shoots right up almost to 1,000,000, but then a few milliseconds later drops down again. Can you go even higher than that? And the answer is yes. Scientists have gone to even higher magnetic fields than 889,000 Gauss, the record for the strongest magnetic field that's ever been created on the surface of the Earth, and perhaps the strongest artificial field in the universe, if you think there's nobody else out there, is this magnetic field that was created in the military research town of Sarov in Russia. It was an experiment called MC1, and they reached the magnetic field of 28 megagauss, but only for 1 microsecond. And so here are the data from the paper. Here's a plot of the magnetic field in megagauss versus time. So this is 1 megagauss on this plot. That's only all the way down here. And you can see the field shooting up over a period of about a microsecond. It's going up and up and up, and then suddenly the graph stops. And you might say, what happens after this? Surely it keeps going. The answer in the paper is that the way you get a 28 megagauss magnetic field is by blowing up a bunch of magnets and smashing them together. So as the paper reports, this required 170 kilograms of explosives, and they noted that you need to perform this experiment outdoors. So this is definitely not a multi-shot magnet, it's a one-shot magnet. But if you want to smash magnets together, you can reach a magnetic field of 28 million Gauss. So with that perspective, let's now switch over to astronomy, bearing in mind, so the Earth is 1 Gauss, a pretty strong magnet as far as the Earth goes is 500,000 Gauss, and the strongest magnet we've ever made is 28 million Gauss. So here is how things stack up out in space, and the numbers are really quite extraordinary. They're both much, much, much smaller than magnetic fields that we deal with on Earth, but also spectacularly larger. So these are sort of arranged from the weakest magnetic fields you'll see in the astronomical literature down to the strongest. The weakest ones are the very weak magnetic fields that must exist from processes in the early universe, and the numbers that are talked about in these papers are things like 10 to the minus 30 Gauss. And the strongest magnetic field you can find in literature is that if there is a Planck mass monopole, if such a thing exists, then it would have a magnetic field of something like 10 to the 55 Gauss. So there is 85 orders of magnitude between the weakest and the strongest magnetic fields that astronomers like to think about. 10 to the 20, I'll have to add that one on here. But what's really cool, I think, is that the first one is speculative. No one's ever measured a 10 to the minus 30 Gauss magnetic field. And the last two are also speculative, 10 to the 30 and 10 to the 55 Gauss. But every other thing on here, starting with 10 to the minus 15 and going up to 10 to the 16, all of those have actually been measured. They're all observed magnetic fields. So just if you stick to observations and you don't trust the theory, there's still 31 orders of magnitude between the weakest magnetic fields that we see in the universe and the strongest. So there's a huge range of different physical processes we can study if only we can actually see and map the magnetic fields. So I think I've worked on all of these at some point, from the intergalactic medium through to magnetars. But what I'm going to be talking about to you today is these ones around here, the interstellar medium, the intracostal medium, intergalactic medium. So these are very weak magnetic fields, starting at around a few microgauss, so a millionth of the magnetic field of the Earth, and dropping down to another 9 orders of magnitude below that. Incidentally, just to compare to what I was saying before, so the strength of the Earth's magnetic field is 1 Gauss, so that's about here. It's weaker than all of these diffuse magnetic fields, but there are many stars which have magnetic fields that are much stronger than the Earth's magnetic field. The strongest magnets on the Earth were of the order of megagauss, so we can make magnetic fields stronger than any main sequence star, but we don't even come to within a factor of 1,000 of the most magnetized white dwarf, let alone pulsars and magnetars. So the magnetic fields that we experience on Earth, that we can make on Earth, are both vastly stronger than the magnetic fields that we measure and study in diffuse space, but tiny compared to the magnetic fields associated with compact objects. So how do you see a magnetic field? A lot of things in astronomy, you point a telescope at them and you see them, a star or a galaxy or a planet. But magnetic fields, despite not being anything to do with dark matter or dark energy, you obviously normally can't see a magnetic field when you point your telescope at it. So you have to do so indirectly. And there's a bunch of different ways you can do this, but the workhorse for studying the diffuse medium is this process called Faraday rotation. So most of you know what this is, but just briefly, if there's any students in the audience, this is a plasma effect such that when you shine radiation through a magnetized ionized plasma, the plane of polarization actually twists to some new value. And so the amount by which it twists is described by this equation here, that you start off with some intrinsic angle theta naught, and the angle that you measure is different from theta naught by an amount Rm times lambda squared, where lambda is your observing wavelength. And Rm essentially is the rotation measure. It's how much stuff there is along the line of sight, where stuff is defined as free electrons and magnetic fields. So the more electrons you have along the line of sight, the more magnetism you have along the line of sight, and the longer your line of sight, the more rotation you get. And also, because there's a lambda squared term, the longer the wavelength, the more rotation you get. So to put some numbers on this, if you observe the sky at a wavelength of 1 meter, as you can see from the lambda term, this is a big effect at radio wavelengths and a negligible effect at optical wavelengths normally. So if you observe at a wavelength of 1 meter, and you take a slab of the sky, which is 3,000 parsecs in length, has a typical interstellar magnetic field of 3 microgauss, and has an electron density of 0.03 electrons per cubic centimeter, those are all pretty typical numbers, then the amount of rotation you get is 220 radians. So the polarization twists around about 30 times over 3,000 parsecs. So it is quite a measurable effect. It's not a subtle effect. You can just sort of see by eye when you actually look at the data, the angle twisting as you move from one wavelength to the other. And so here's an example of it right here. This is some data from my thesis on a polarized object. It really doesn't matter what the polarized object is, as long as you're producing polarization and then it shines through some foreground magnetized medium. So here is data on a pulsar, which is polarized, and if you measure the angle theta at many different values of lambda, you can see this linear effect. Theta evolves as a nice straight line as a function of lambda squared. It wraps around every 180 degrees because polarization is only defined modulo 180 degrees, and all you have to do is just fit a straight line to a bunch of points, just like in high school or undergraduate days, and you get out the slope, which is the rotation measure, in this case 495 radians per square meter. And so if you plug it into this formula, you can work out something about the magnetic field along the line of sight. So there's a couple of really profound things about this. Firstly, not only does it prove to you that the fact that there's a slope here proves to you that there is invisible magnetism in the gas between the pulsar and you, but it also tells you which direction the magnetic field is pointing in. Because this is not a subtle effect that involves lots of sort of Bayesian fitting. If the slope is positive, then the magnetic field is positive, and you can imagine a different measurement where the slope was negative and the magnetic field is therefore negative. And the way it's defined as a positive field is one that's pointing towards you, and a negative slope is one that's pointing away from you. So in this case, just by instantly looking at the data, we have measured the direction of the magnetic field between us and this distant pulsar. The average magnetic field in this slab of interstellar space has a line of sight component directed towards us. The other thing is, because this is an effect that really dominates at radio frequencies, radio waves don't tend to be attenuated by extinction or dust or anything like that under most circumstances. So the universe is entirely transparent as long as you've got a polarized background source. You can measure the magnetic field anywhere you want in the universe. And fortunately, nature has given us many distant polarized sources, and so we can measure the magnetic fields over large distances. Even taking this to its extreme, the cosmic microwave background, the most distant thing we can see in the universe, the CMB is polarized. So if you have a good enough telescope, you could actually measure the Faraday rotation of the CMB, and then you have an integral over the entire universe, and you can measure the line of sight magnetic field of everything. Unfortunately, because the CMB is bright at millimeter wavelengths, where lambda is very small, it's a tiny, tiny effect, and no one has yet measured Faraday rotation against the CMB. But that's an experiment for the future. Was there a question somewhere? Okay, so the experiment that people have been doing since the 1960s is you find some background polarized source. You really don't care what it is, as long as it's polarized. So conveniently, there are these polarized radio galaxies all over the sky. You measure the Faraday rotation of that signal, and it tells you something about the object in the foreground. The problem with this experiment is that the formula is just an integral. So you don't know where along the line of sight the rotation that you see is occurring. If there's multiple objects along the line of sight, you can't separate them because you just get one big integral along the line of sight. So this is the old way of doing things that was very fruitful, but was started in the 1960s. But the new way of doing things that's only been possible for the last 10 years or so is an approach called the rotation measure grid, whereby using wide fields and high quality polarization calibration, you don't just get one radio galaxy through the object you're interested in, but you get many sources, dozens or hundreds or thousands of objects, background objects through the object you're interested in. And this allows you, through various statistical effects and through different inclination effects, to be able to isolate in space the object you're interested in and learn something about the three-dimensional geometry of a particular localized object. So a lot of what I'm going to be talking about for the rest of this talk is about the rotation measure grid and all the different physics that you can get from it. What I'm not going to spend a lot of time talking about is the actual observational technical measurements. That is extremely challenging just to get to these data points. Polarization calibration is extremely messy, and the way in which you measure these rotation measures, unfortunately, is not really as simple as fitting a straight line to it, as Cameron and Shannon and others can tell you. It's quite involved, and I'll skip all over the technical details. If you're interested in that, you can ask me at the end. But let's just suppose that you're able to get these beautiful data. What can you do with them? So let's start off with a situation like this. Let's start off with, in our own Milky Way or nearby, and let's suppose there's just some blob, some object we're interested in, and we want to understand its magnetic fields. If you look at nearby blobs, what sort of blobs do you see and what do you learn about them? So here's a very nice recent example that was just accepted a week or so ago by a student I've been working with, Sarah Betty. And this is a very large object that's falling into the Milky Way called the Smith cloud. It's this huge cloud of neutral and ionized gas that is a particularly large nearby example of these high velocity clouds, these mysterious clouds in the halo of our galaxy that are traveling at high speeds and are sort of raining down from above. And this is about the state of the art that we can do right now. I'm not sure how many galaxies per square degree Sloan gets, but it's some enormous number, and with these new surveys we're going up much larger. Well, the polarized sky is reasonably sparse, and the state of the art that we can do right now is about 3 sources per square degree, which isn't a lot, but it's a lot more than we could do in the past, and it's a lot less than we're going to be able to do in the near future. But with 3 sources per square degree, you get something like this. So let me explain what this graph is. The grayscale is the Smith cloud. You can see it here. The red and blue symbols are the locations of background radio galaxies. These are galaxies that have nothing to do with the Smith cloud. They're billions of light years away. They couldn't care less about us, but they all happen to be polarized. And for each one of them, we can measure the Faraday rotation along the entire line of sight from this distant radio galaxy all the way through the universe to us. And it turns out that in this case, most of the Faraday rotation that you measure is happening right at the last stages as it travels through the Smith cloud and through the Milky Way. A blue symbol is a case where the magnetic field is pointing towards us. A red symbol is where the magnetic field is pointing away from us, and the size of the symbol represents the strength of the rotation measure. So what you can see are places where the rotation measure is quite low, like here, and there's places like here where you can see the rotation measure is quite high, and you can see places where the rotation measure is consistently positive, and you can see places where the rotation measure is consistently negative. And so what Sarah did in this case is she used the VLA to map out about 3,000 polarized background sources. And so just by sheer weight of numbers, we can't control where these radio galaxies fall. They're sort of randomly distributed. But by sheer weight of numbers, we can actually define the magnetic field of this cloud. So the first thing you can see is that the cloud does have a magnetic field. The circles off the cloud are systematically smaller in size than the circles through the cloud. They're not zero because it's inside the Milky Way, and the Milky Way also has a magnetic field. But there's a clear excess associated with the Smith cloud. And you can see there's some structure to it. It's sort of generally positive here and negative here. And what you can do with a simple model is you can actually show that this pattern is consistent with a cloud falling into the galactic halo and the galaxy's magnetic field wrapping, draping around the cloud, the front end of the cloud, as it falls into the Milky Way. But what's really nice here is that you can actually show that the magnetic field strength of this draping structure is actually quite strong. It's about 5 microgauss. And this is surprisingly strong. And this answers one of the questions about how high velocity clouds can actually exist. One of the problems is that you know how long it takes the cloud to fall into the Milky Way, and it's a long time, it's like millions of years. But you also know how long it takes for the cloud to be, you know the mass of the cloud, and you know its velocity, so you can work out how long it takes to be tidally stripped as it moves through the halo. And the answer is generally that the timescale of destruction is quite small. So one of the problems with understanding high velocity clouds is how do you keep them from being destroyed? How do you make them live longer than they should? And we seem to have, here and in a couple other cases now, seem to have the answer that it's magnetic fields. The magnetic field both protects the cloud, slows down the process of stripping, both through inhibiting thermal conduction and also by draping. And so by having this magnetic shield, the clouds can actually survive to get all the way down into the disk. Here was another surprise. This is work done by my recently graduated PhD student, Jane Kaczmarek, who submitted her thesis just over a year ago. Here is a wide field view of the large Magellanic Cloud, which is one of the satellite galaxies of our own Milky Way. This is just the edge of it. And here is the small Magellanic Cloud down here. And this grayscale shows neutral gas. There has long been known to be what's called the Magellanic Bridge, which is this weak bridge of gas that actually joins the small Magellanic Cloud and the large Magellanic Cloud and shows them to be part of the same bound system with tidal stripping going on because of their interaction between each other and because of their interaction with the Milky Way. In this case, we were able to measure the Faraday rotation from 167 background galaxies. And again, there are much larger circles through the bridge than off the bridge. And you can see that through the bridge, the circles are consistently large and blue, and off the bridge, they're small and of random sign. And so what we have done here is made the first ever measurement of the magnetic field in the Magellanic Bridge. It's relatively weak. It's just the ordered field is a fraction of a microgauss, and the random field is about 1 microgauss. But the field actually seems to be running along the bridge. And so what we seem to have here is we revived an old idea that was sort of dismissed in the 60s and 70s of a pan-Magellanic field. That whatever created the magnetic field of the small Magellanic Cloud and the large Magellanic Cloud, it's all part of the same ensemble, and that as they interact, we're actually stripping off that magnetic field and it's stretching out between them. Besides the Magellanic Bridge, there's also the Magellanic Arm, which goes beyond both the clouds almost all the way around the sky, and the next step, which is obviously much harder, is to actually measure the magnetic field of the Magellanic Stream and see if the whole thing is this giant magnetic flux tube. So that's what you can do in individual objects. There's lots of others of these. These are just sort of 2 of my recent favorites, but you can see all sorts of new physics that you can get from mapping out magnetic fields in these large-scale structures. So as I said, if you've got some sort of cloud of gas in the sky, you can find sight lines through it and measure its magnetic field. And the bigger the object, the more sight lines you get and the more you can say about it. So this object is about 10 degrees across, and this one is 20 degrees across. Why not go bigger? What's the biggest thing you can study on the sky? Well, the biggest thing you can study on the sky is the entire sky. Why not map out these sight lines over the entire sky and map out the geometry of the entire Milky Way as seen from the inside? We would really like to know what the Milky Way looks like. If I just exit out of my my talk, here is a geometry, the magnetic geometry of the galaxy M51, and you can see it's beautiful. It seems the magnetic field seems to follow the spiral arms and gets messed up by its interaction with its companion. Well, what does our own Milky Way's magnetic field look like? And as always, this is a harder question to answer because we're doing it from the inside. But finally, after years of arguing, we seem to be getting a coherent picture. So here is a reconstruction that Niels Opperman, who used to be here at CITA, and I and others did, to take 40,000 sight lines through the whole sky and to essentially smooth them and to generate an all-sky map of rotation measure. And what you can see in this is that there's some large-scale features that correspond to the overall geometry of the Milky Way, like this big blue patch here. But there's also some individual discrete features which represent foregrounds. And if you zoom in on these foregrounds, you can just see how complicated they are. Here is a zoom in that we did with my former postdoc, Cormac Purcell, of this large feature here called the Gum Nebula. And you can just see how complicated things are. It actually turns out that most of the magnetic field here is negative, mainly blue, but you can see the sharp change to red as you move on to the Gum Nebula. But there's also red stuff here as well. It goes from blue to red without a foreground object, and it goes from blue to red with a foreground object. So figuring out what's foreground and what's large scale is very hard. Now people used to get into huge arguments about this, but supposedly the final word came a few years ago in this paper by Jansen and Farah. They just took all the data available, 40,000 points and all sorts of other data sets. They just stuck it into giant code and they just inverted the whole thing. And what they got was this, which at the time I think we all agreed was what the magnetic field of the Milky Way actually looks like. So obviously it's a three-dimensional model, so this is just one slice through it. But if you look at a slice through the galactic plane, this is supposedly what it looks like. The galaxy is remarkably simple. That most of the Milky Way has a clockwise, the magnetic field follows the spiral arms, more or less. It's clockwise over most of the galaxy, but there's this one strange section involving a couple of spiral arms where the field's actually reversed, where there's some sort of current sheet that reverses the magnetic field, but just along these two spiral arms where it's going counterclockwise. So that's sort of a picture that everyone sort of converged on, but it looks like it maybe that's too good to be true, and we still don't have the final story. If you now look at this region here, a lot of the argument about this geometry comes from the fact there's a sort of a butterfly pattern here, that there's a red patch here and a red patch there and a blue patch here and a blue patch here. So there's this sort of anti-symmetry with diagonals matching. But it turns out that if you look more carefully, this red patch here is actually this feature here, which is actually dominated by a local feature, the North Polar Spur. And so it turns out that what we thought was actually a large-scale part of the Milky Way actually is just an individual foreground feature. And then it also turns out that this region here hasn't been that well studied, and maybe these data are not that reliable. So the answer to what does the large-scale magnetic field of the galaxy look like is still ahead of us. There's a big new data release coming out in the next couple of weeks that much better samples this patch here in the southern sky, and there's a large international project called Imagine, which is trying to pull all the data together in a Bayesian way. So in the next year or so, we should have a much bigger picture and much more confidence of what the three-dimensional magnetic field of the Milky Way actually looks like, both in terms of the small-scale individual foreground features and in terms of the large-scale geometry. And this is very important because once we understand our own galaxy, we can actually then start putting it in the context of all the other galaxies that we see, for which we have better statistics, but much worse detail. It depends who you ask. I think the answer to that is yes, you can rule out a large number of reversals, but there's at least one group in Beijing that argues that there is a very large number of reversals, one between every arm. But in my opinion, Cameron, I don't want to put you on the spot, but I think you agree with me that the evidence is that there's probably just one major reversal in the Milky Way. Sorry, Tova was first. Yeah.
You all done any comparisons with the cosmic ray and information out of Ice Cube and other?
I mean,
I know it would be hard to sort of.
It's hard to break the degeneracy at the moment. At the moment, you can use this model to predict the cosmic ray anisotropies, but it's hard to actually incorporate those into the model. But I think Imagine are trying to do that. I'm not part of that project, but I think they're trying to do that. Alisa?
There was a photograph speaker a few years ago, I found her name. She did something where it was also like, you naturally assume that you have some sort of consistency along the spiral arms, and there was something where it broke that assumption. Yeah.
I'm not sure.
Because that's just the the magnetic field is weird.
Well, are you asking why does it reverse?
I mean, it just, does that, I guess the assumption, like, if you have to have consistency along the spiral arms, is that a concept?
Oh, right. I think that sort of naturally comes out of sort of dynamo theory, and that the field, we think the field comes from a dynamo, although we don't understand what type of dynamo. And the dynamo is some combination of turbulence and differential rotation. So differential rotation naturally sort of drags it out along the spiral arms, but it's true that the pitch angle does not have to align with the pitch angle of the spiral arms. So it's not a perfect alignment with the spiral arms, and it's not necessarily even the same spiral arms as the one you see in the optical. Sometimes they are, like this, where it clearly seems to follow, but there are other examples where the magnetic arms actually lie clearly between the starlight spiral arms. Was there something you want to add to that, Cameron? You've looked into this in a bit more detail.
Well, I mean, I've done some modeling that looks at not following arm symmetry, and that seems to also fit quite well. A lot of models just follow the arms because people like the symmetry arguments. People like how pretty spirals look.
Right. So I think it's fair to say that in the Milky Way that the magnetic arms are within a few degrees of pitch angle of the spiral arms, but probably not exactly. They're within a few, or you're not even convinced? Yeah. Pardon? Probably as good as the cows, yeah. Was there another question? Okay, so so let's keep going. So we've looked at our own galaxy. What about other galaxies? So can you use, if you pick a polarized background radio galaxy, can you use it to say things about other things along the line of sight besides the Milky Way and clouds of our own galaxy? So under certain conditions you can. Normally if you see one radio galaxy, so here in the picture I just showed you, you've got thousands. But what if we just pick one of these? Is there anything we can say about the magnetic field in that along that sight line? So under certain conditions, the answer is yes, you can. And so what we did after we came up with this idea years ago and spent years looking for the right source. But a couple of years ago, we finally found a source for which this worked. We found a background polarized source that experienced gravitational lensing. And so the idea here is that there's two different. So the source has been split into two, and both components are polarized, and they both show Faraday rotation, but they show different amounts of Faraday rotation because they've been lensed through some intervening galaxy, and the path that they've followed through the intervener is different. So everything about the sight line is identical, except for the part where they travel through the intervening galaxy. So we found this lens polarized source, so the lens at a redshift of 0.4, and here is a graph showing you the two different Faraday rotations that we measure to the two different sight lines. So one of the sight lines goes through the disk of the lens galaxy, and one of them goes through the outskirts of the galaxy, and you can see that they have different Faraday rotations. The one through the disk has a high rotation of several hundred, and the one through the outskirts has a rotation of essentially 0. So by differencing these and also comparing the essentially the heights of these and the area under them, you can work out both the ordered and the random components of the magnetic field in this galaxy that's a billion years younger than our own. And what you find is that the magnetic field in the disk is about 10 microgauss, and that the disordered field is about 15 microgauss. So this is sort of surprising. This is at a much earlier cosmic time by magnetic standards than us. And the galaxy, for example, has rotated 4 times fewer than the number of rotations that our Milky Way has had. And so you expect, if you believe in dynamo theories, that this magnetic field should be somewhat weaker than, maybe e to the 4 times weaker than the magnetic fields that we see in our galaxy and other galaxies today. And yet these numbers are totally normal. They suggest that galaxies back then didn't have a magnetic field that's much different from the magnetic field that we have now. So what this suggests, at least in the sample of 1, which we obviously hope to improve, is that the dynamo are saturated at these typical numbers before a redshift of 0.4, and that magnetic fields have essentially stayed constant ever since then. This allows you to put an upper limit on the e-folding timescale of a dynamo, and as always in astronomy, it's right at the limit between something really interesting and something really exotic. That we have constrained the speed of the dynamo to be faster than 240 million years, which is still slow enough that it could be galactic rotation, But if we can knock this down by another factor of 2 with a higher redshift observation, then we start to require an exotic dynamo that operates through some other mechanism. So while this particular object doesn't allow us to distinguish between dynamo mechanisms, it shows us a clear way with more data that we can actually do this and just work out what sort of dynamo mechanisms operate and how quickly magnetic fields were established in the universe. Were there strong magnetic fields at a redshift of 2 or not? This sort of object is the key to doing that. The other way in which you might get a handle on things is not by looking at the magnetic field of individual galaxies, but looking at the diffuse magnetic field of the intergalactic medium, which perhaps came from pollution of individual galaxies and AGN shooting out their jets and their supernova explosions and splattering their magnetic field into the cosmos. And one way in which you might be able to measure the rotation measures of the intergalactic medium is through fast radio bursts. The first ever Faraday rotation of a fast radio burst was done by a team here at CITA, and now there's been another 5 or 6 that have been measured, and Ryan McKinven, a student here, is hoping with using CHIME to measure the rotation measures of many, many fast radio bursts. So we're just on the edge of having a very large number of new rotation measures from fast radio bursts. And what's exciting about fast radio bursts is that you don't just get a rotation measure like we do for a background galaxy, but because it's a pulsed event, we also get the dispersion measure. And with the dispersion is just a count of the number of electrons along the line of sight. So the problem with the rotation measure is there's always a degeneracy between having lots of electrons and lots of magnetic field. Under most circumstances, you can never distinguish the two. And the way in which we get magnetic field numbers is by using other data like X-ray absorption data. But if you have both an RM and a DM, then in principle you can just divide one by the other and the ends disappear and you get the magnetic field. So pulsar people have known for decades that if you want to measure the magnetic field in the Milky Way, you find a pulsar, you measure its rotation measure, its dispersion measure, and you just divide one by the other and you have the magnetic field. So the question is, can you do a calculation like this for fast radio bursts? And the answer is almost. What we showed is that the problem with doing this for fast radio bursts is that unlike the Milky Way, the rotation and the dispersion are not coming from the same gas phases. The rotation measure is coming from a highly magnetized phase, and dispersion measures coming from a dense phase, and they're not the same phases. So if you divide the RM by the DM, you're dividing apples by oranges, and you don't get the right answer. But you can fix this. So here is a simple simulation of the universe where we seeded a universe with magnetic fields and let it evolve. And this is the magnetic field of the intergalactic medium in nanogauss as a function of redshift. And you can see it's pretty boring in this case. The magnetic field's about 10 nanogauss at all redshifts. If you just detect a whole lot of fast radio bursts, correct for their hosts, and you naively divide RM by DM, then this is what you would reconstruct, which is obviously wrong. But if you make a very slight correction where you correct for the average redshift of the filaments and you correct for the fraction dispersion measure in filaments, which actually just come directly from whatever cosmological model you adopt, you don't need to make any measurements here, then if you now apply it to a bunch of fast radio bursts, you can actually successfully reconstruct the magnetic field of the intergalactic medium. So what Ryan is hoping to do is to get a bunch of fast radio bursts to boring galaxies where there's very little contamination from the host, and then use that ensemble to, and this formalism to actually reconstruct the magnetic field of the intergalactic medium. And once you know the strength of the field of the intergalactic medium and you know how it's evolved with redshift, you can really get a very good handle on the magnetization history of the universe. So that's what you can do with one source or a few sources. What do you do if you have lots and lots of sources? If you want a very large number of background sources like I had in this picture here, then you can't really use these to measure the magnetization of the universe unless you actually know the distance to each of these sources if you have all of their redshifts. Measuring redshifts to radio sources is hard because there isn't really a spectral line in the radio, so you have to match them up with optical sources and then do a correlation. But if you could do that, if you can get redshifts to your radio sources, where's my pointer not working? Then instead of having an integral of NBDL, over cosmological distances you now have redshift effects. And this makes life hard because faraway sources, the expansion of the universe dilutes the rotation measure by a factor of 1 plus z squared. So the distant rotation measures shrink and the foregrounds stay the same, and cosmological magnetic fields get harder and harder to measure the further away you go. So you need lots and lots of sources. So this is what we're trying to do. With my student Alison Hammond, we were able to extract about 4,000 sources in the literature that both have a rotation measure and a redshift. The rotation measure coming from radio waves and the redshift coming from optical spectroscopy. If you take all 4,000 sources and plot rotation measure versus redshift, you have integrals, this integral through the universe going all the way up to redshifts of 5. But the problem is that you can't really see much of a trend here. The problem is you're looking at all sorts of different sources taken with different surveys, and it's just a big mess. So what you have to do is you have to now, with this large sample, pick out subsamples that actually make sense and use those to see if you can see any effects. So we're just starting to do this, but here's sort of the first result of this, and this is a first result, and Ariel Amaral, who's a student here, is going to be expanding on this for her thesis. What we did is we took a catalogue of quasars that have show magnesium to, or high quality quasar spectra that either do or don't show magnesium lines in their spectrum. And magnesium is an absorption line that traces relatively dense gas, meaning there's some sort of galaxy in the way. And so there's 599 sources for which there's a good spectrum from Sloan, and for which there's polarized radio emission and a rotation measure. 201 of them show at least one or more magnesium lines, and importantly, 398 of them are quasar spectra that don't show any magnesium. So you can point to that sight line and say there is no intervening galaxy over billions of light years to that particular one, to that particular background quasar. And so when you do that, this is what you get. This is a cumulative histogram showing you how the rotation measures are distributed when you have no magnesium along the line of sight, when you have one magnesium absorber along the line of sight, when you have 2, 3, 4, or even 5 magnesium absorbers along the line of sight. And you can see quite clearly at about 3.5 to 4 sigma that the rotation measures increase when you put absorbers along the line of sight. So this is different from what I showed you in the last slide where we were studying one object. This is a statistical effect. But what we're seeing is that on average, sight lines that have absorption lines have a higher rotation measure than sight lines that don't have absorption lines. In particular, in the rest frame, sticking an absorber along the line of sight increases the rotation measure by about 24 radians per square meter. For a mean redshift of these absorbers is at a redshift of about 1. So this is a much higher redshift than we're able to do for an individual source. And this is really quite remarkable because these sight lines aren't going right through the galaxy. If it did, it would be a damp Lyman alpha absorber or something like that. These are just skirting the far outer halos of the galaxy, and yet we're measuring a very strong magnetic field. So typically where our sight lines have an impact parameter of about 50 kiloparsecs, and yet we're measuring a magnetic field which isn't just coherent but also strong with a magnetic field of about 2 microgauss, which is arguably even stronger than the magnetic field in our own Milky Way's halo. So this is a cosmic, sort of getting towards cosmic noon. And what we seem to be seeing here is that, as we see in a few examples in our neighborhood, like M82, we're seeing very highly magnetized outflows. We're seeing coherent magnetic fields being expelled from galaxies at a high rate. And this also suggests that a rapid magnetic field growth, because in order to expel these magnetic fields, you have to create them in the first place. So already by a redshift of 1, you've got surprisingly strong magnetic fields. I was going to talk more about what we can learn about the magnetic properties of the galaxies themselves, but since we're getting towards the end of time, I'll come back to that if anybody's interested. And just jump to what we're doing right now. So right now there's a lot of excitement because after years of planning, we're finally getting data from these 2 surveys, POSSUM and VLAS. POSSUM is a survey happening in Australia called the Polarization Sky Survey of the Universe's Magnetism, for which I'm the PI. And it's a survey of 3/4 of the entire sky, down to 20 microjanskis, 10 arc-second resolution. So if those numbers don't mean anything to you, another way to put it is that the state of the art right now is that we get about 1 polarized source per square degree. And POSSUM will take us into a regime where we get more like 100 sources per square degree. So we will be able to study the level of detail that you're seeing now. We'll be able to study it to objects that are 100 times smaller or to 100 times more objects. So this is just going to be an absolute goldmine for all of us in terms of being able to map out magnetic fields using the techniques that I've described, plus some more advanced techniques all over the universe. So this is what's happening in the southern hemisphere. In the northern hemisphere, we have VLAS, the Very Large Array Sky Survey, and it's designed to be sort of a companion. It operates, it's not as sensitive, but it's at higher angular resolution and operates at a higher frequency. And one way of understanding this is that if you observe at low frequency, you learn about the foreground, so you study clouds in the way. And if you observe at high frequency, then you learn about the intrinsic properties of the sources themselves. So there's a nice overlap of sky between the two, about 10,000 square degrees, where we'll get about 60,000 sources, of which several thousand of these will have redshifts and optical spectra, where we can simultaneously learn about the source itself and about the intervening medium. This is going to generate an incredible complex truckload of data because you have very high spectral resolution in multiple Stokes parameters to a very large number of sources across very broad bandwidth. So we've also got a separate initiative happening here, which Cameron is part of the team working on, called CITA, the Canadian Initiative for Radio Astronomy Data Analysis, which has been underway for about 6 months now. And the idea here is to take these very complex data sets in polarimetry from VLAS, from ASCAP, and also from CHIME, and to turn it into something digestible and user-friendly and easy to interact with, so that we and everybody else can pull magnetism out of the sky without having to be black belt polarimetry experts. And even though my original motivation was polarimetry, there's a whole bunch of other things that we're going to do as well, involving transients, continuum, pulsars, H1 absorption, and all sorts of other things too. And if you're interested, you can talk to me or Cameron about all the things that we're doing. But the bottom line is that these radio telescopes are now producing extremely complex survey products. And if you want to be able to, the plan is we want to be able to make it Sloan-like, where you can just click on a point in the sky and get all this simple information, rather than all the horrible, messy radio astronomy that we all have to live with at the moment. So to sum up, I hope I've convinced you that cosmic magnetism is a very vigorous and rapidly developing field, that we can touch on a huge range of topics across astrophysics, everything to sort of from high redshifts and early processes of galaxy formation all the way through to the physics of infalling clouds in our own Milky Way. And we're finding a whole range of new and surprising and unanticipated results. The things that I've talked about today is I talked about the rotation measure grid and how you can use that to map out the structure of magnetic field and everything, the interstellar medium, the Milky Way, and other galaxies. And I talked about rotation measures of absorbers and how we can use those to map out magnetic fields over time. One thing I skipped over, but I can come back to if anyone's interested, is depolarization and how you can use that to probe gas and magnetic fields close to AGN. There's a whole range of different experiments you can do depending on your frequency and the data set that you have. But I think the bottom line is that finally, after years of promising and showing artist impressions and simulations, that we're finally seeing what the polarized sky actually looks like because of all these new fabulous surveys and experiments. And this is just the beginning. We're turning on these new projects like ASCAP and VLAS, both of which are just warm-ups for an even bigger project, the Square Kilometre Array. And in the next decade, we're truly going to be able to explore the magnetic universe. Thanks very much. Right.
The MG magnesium system, so that I was expecting with more and some would be pointed in random directions. So what is the additional part?
Yep. That's right. So you get reversals if you have more than one object, and so that increases the dispersion. It basically is just a random walk. You just get an increase, but it's slower and just increases as root n. And this is the absolute value of the rotation measure. So it pushes it positive because we're taking the absolute value. But yes, there is a reversal, not just by adding more absorbers, but even one individual absorber might have reversals along a line of sight as well. So it slowly grows, not linearly, but as the square root as you add more absorbers. Chris?
These higher resolution arm data more of sources of scattering, sort of scattering of radio losses.
Not really. We can probe turbulent scales with these sort of data, but the scales tend to be relatively large, about 1/10 the resolution element. So that tends to be much larger than the scales that you'd be interested in for scattering. But I think for fast radio bursts, where you have scattering and rotation and dispersion, then you can perhaps learn about all of those processes on the same scales. But for your sort of classic AGN experiment, I don't think you learn too much about turbulence on the scales that you'd be interested in. You do learn a lot about turbulence, but on sort of scales of kiloparsecs. Questions?
About the FRB, is that like you assume that all the RN and DM are coming from the IGN and there are filaments and all contributions are like supposed to have common like that?
Yeah, so this is a Magnetohydrodynamic cosmological simulation, which includes galaxy halos and clusters and filaments and voids. It doesn't have any contribution from the host galaxy. So in order for this to work, you have to remove the contribution due to the Milky Way and also the contribution due to the host. So you can do that in a statistical sense, which means that you need more data. But there's also, at least even from the small number of FRB, polarized FRBs we already have, there does seem to be a sample that have very small rotation measures that suggest that there isn't any contribution from the host. And for the first repeater, where you could localize the host, you can actually work out what contribution has to be from the host. I should note that there was a conference in Israel last month where the Australians presented 2 new localized fast radio bursts that are not repeaters. And as was presented at the conference, at least one of them seemed to be an elliptical galaxy, which is sort of strange. We don't understand why that would be. But if that's true, then those you'd expect there to be almost no host contribution at all. And those, if there are more of those, that'd be a really great probe of the IGM. But the beauty of CHIME is that we'll just get lots and lots of these, both repeaters and not repeaters. And we should be able to identify different subsamples and pick up the ones that are best for probing the IGM.
So the goal is to considering the average magnetic strength and the filaments?
So the simple goal is to calculate the mean as a function of redshift. But when you have a large enough number, you can both look at the mean and the variance. And that allows you to work out both a mean strength for the field and a turbulent component as well.
So you really need FRB of high redshift.
Right, so the FRB, the one FRB that we have a redshift for is all the way down here. This is a bit optimistic going all the way out to a redshift of 6, but certainly even if we could fill in this regime here out to a redshift of 2, it'd really start to distinguish between different models for the magnetization of the universe.
Questions? Okay.
Thank you.